Defining a topology on a finite product is a core task in introductory topology. However, as the number of dimensions approaches infinity, mathematicians must choose a definition that preserves the properties of the individual spaces without violating the axioms. Consider the standard product topology on two spaces, X and Y. Its basis consists of products of open sets U and V. This works because the intersection of any two basis elements results in another basis element. We can also define this space using subbasis elements and projection maps. As illustrated in Figure 15.2, intersecting a finite number of these infinite strips, one horizontal and one vertical, recovers the exact open basis rectangle used in our first definition. While both methods yield the same result for a finite product, the second method, defining the topology through the pre-images of individual coordinates, provides the mathematical framework necessary to handle products with infinite dimensions. Consider an arbitrary index set J and the Cartesian product of an indexed family of spaces. When the index set is infinite, we are faced with two distinct ways to generalize our definition of openness. The first is the box topology. Here, a basis element is formed by taking the product of an infinite number of open sets, one from each coordinate space. In this topology, a basis element places a specific restriction on every coordinate simultaneously. It requires every single dimension to stay within its own specified open set. The second option is the product topology, which is generated by the subbasis of projection mappings. In the product topology, a basis element only restricts a finite number of coordinates. For all other indices, the set is equal to the whole space, meaning there is no restriction on those dimensions. Theorem 19.1 states the box topology is finer because it allows infinite restrictions. They are identical only for finite products. Conventionally, mathematicians assume the product topology for infinite cases because it preserves essential mathematical properties. This preference is not arbitrary. While the box topology is a valid construction, it fails to preserve compactness, a property central to many proofs in higher-level analysis and geometry. To see why the product topology is preferred, we must first define the property that it is designed to protect: compactness. An open covering is a collection of open sets whose union contains the entire space X. A space is defined as compact if every open covering of that space contains a finite subcollection that also covers the space. If you cover a space with an infinite number of overlapping open sets, and that space is compact, most of those sets are redundant. You can remove the excess and still cover the entire space using only a finite number of those original sets. We can also define compactness using closed sets and the finite intersection property. A collection has this property if the intersection of any finite subcollection is non-empty. Theorem 26.9 states a space is compact if every such collection has a non-empty overall intersection. Compactness ensures that properties that hold for the finite parts of a space can be extended to the space as a whole, preventing infinite coverings from becoming mathematically unmanageable. Tychonoff's theorem is the bridge between these two concepts, answering whether the product of compact spaces remains compact. The theorem states that if each individual space in an indexed family is compact, then their product is also compact, provided we use the product topology. The restriction to the product topology is necessary. The theorem does not generally hold if we use the box topology for infinite products. To prove this, we use the finite intersection property. We begin with a collection of closed sets in the product space that has the FIP. These closed sets are projected into each coordinate space. Because the projections satisfy the finite intersection property within each compact factor space X alpha, their intersections are non-empty. This guarantees we can choose a coordinate X alpha for every index alpha. By combining these coordinates, we assemble a point X in the total product space. The goal of the proof is to show that this point X lies in the closure of every set in our original collection. We test this by checking every neighborhood of X. In the product topology, these neighborhoods are formed by basis elements. Crucially, a product topology basis element only restricts a finite number of coordinates. Since our set's intersection is constrained across only finite dimensions at once, point X satisfies the conditions for every set, proving the product space is compact. Tychonoff's theorem reveals that the product topology is the unique structure that allows finite compactness to scale into infinite dimensions. To demonstrate why the product topology is required, we can look at a counterexample using the box topology. Consider an infinite product of the closed interval from -1 to 1. This space is compact in the product topology, but not in the box topology. In the box topology, we define an open set U where the nth coordinate is restricted to the interval from -1 over n to 1 over n. Because it restricts every coordinate, this set shrinks toward 0 simultaneously. This creates an open set that is too restrictive for the rest of the space to be covered by any finite number of similar sets. As a result, we can construct an open covering of the space that has no finite subcollection, proving that the box topology fails to preserve compactness in the infinite product. This illustrates the fundamental trade-off. The product topology's finite restrictions allow it to preserve compactness, while the box topology's infinite restrictions do not. For students preparing for exams like the CSIR NET or GATE, remember that the properties of an infinite product space depend entirely on which topology is assigned to it. When evaluating an infinite product of compact spaces, the first step is to identify whether the space is equipped with the product or the box topology. Do not apply Tychonoff's theorem to a box product. The product topology is the standard for infinite products because it ensures that the core properties of factor spaces remain intact at scale. If you found this technical breakdown helpful, like the video and subscribe for more in-depth explorations of topological theory.